we're going to simplify this. This is a square root of 25, a to the 4th, b to the 9th. The first thing we need to do is we need to break everything up into factors of squares. In other words, 25 is a perfect square. So we're going to write it as 5 squared. We're going to write it as something squared as much as possible. A to the 4th is going to be written as a squared squared. B to the 9th, well, we're going to have to break that up into 2 pieces. B to the 8th times b. Now the b to the 8th can be broken up as b to the 4th squared, and then we got the b. So this b on the end is the only thing that that's not a factor that's a square. We have a factor that's a square, we have a factor that's a square, and we have another factor that's a square, and then we have the b left over. So that means that this guy is probably going to be the only one that won't get brought outside the radical. Remember, this is a square root. So whatever this number is what we have to have a factor of. If it's a cube root, we need factors of cubes. So then visually, it's easier to see that if you take each one of those factors and put them underneath their own radical, which you're allowed to do, since it's all multiplication, then it's easier to see that the square root of 5 squared is just 5. The square root of a squared squared is just a squared. The square root of b to the 4th squared is just b to the 4th. And then the little radical b on the end stays underneath the radical. Some of you can go straight from this to here and skip this middle step. But if this is challenging for you, you need to show as many steps as possible. You need to work it out on notebook paper. You will learn it better if you work it out on notebook paper. So these, if you're taking notes right now, put them on the back of this worksheet. This is a cube root. So now we need to break it up into factors of cubes. So 125, you may have to experiment on your calculator with figuring out if there's a perfect cube within 125. Some of you may know what's 5 times 5 times 5. 125. So that means 125 is 5 cubed. Okay? M to the 30th can be written as what cubed? 10 and 3. That's right. So 10, m to the 10 to the 3rd. Now the 20 is going to have to, p to the 20 is going to have to be broken up as p to something that's divisible by 3. Is 20 divisible by 3? Is 19? Is 18? Okay, so we need the p to the 18th times the p to the 2. That'll give me the p to the 20. Now the p to the 18th can be broken up into 6 times 3. And then the p squared is going to have to be left by itself. So he's probably the only one that won't get brought outside the radical. This cube root will cancel out with that cube, and that cube. It'll cancel those 3 things off. Now they're probably going to show that you break them up into their own cube roots. And that's fine. Visually that may help you. When they're all multiplication, you can give them their own cube root. And this cancels that, this cancels that, this cancels that. This one doesn't have anything to cancel with. So what's in parentheses is all you have left when you take the cube root off. And then the cube root of p squared is going to be left on the end. Break it down. Might be easy to look at the answer choice and figure out the answer, but it'd be good for you to just break it down as if it wasn't multiple choice. So that'd be right. Okay. Let's try another one. Okay. Now, this is a little bit new, where we have to, well, may not be yet, where we have to rationalize the denominators. Have we ever rationalized the denominator before? Can't have a radical in the denominator. I'm not sure if we did any of that in Algebra 1 or not. So, if we're going to simplify through division, it works the same way as multiplication. We still need to break them up into something squareds, into quotients of squares rather than factors of squares. Y to the 8th, and they do it this way to maybe help you visualize it. Give, just like in multiplication, if they're factors, you can give them their own radical. If it's division, you can put the top on a radical and another radical on the entire denominator, and it'll be the same thing. So now when you break the y to the 8th down, that's easy, times 2. 8 is 4 times 2. Y to the 7th, you break it down the same way. You got a 6 and a 1, and the 6 breaks up into 3 times 2, and then you still got it times x to the first. So it works the same way. You just focus in on the numerator, focus in on the denominator, do them the way we did them on the previous problems. Ends up looking something like this. X to the 4th, I'm sorry, y to the 4th over x to the 3rd root x. But the problem is that your denominator has to be a rational number. And square root of x would not be considered a rational number. So we have to somehow modify this answer so that there is no radical in the denominator. Okay? I'll say it again. The answer you put down should not have a radical in the denominator of a fraction. And so there is a way to manipulate or modify the answer so that you don't have a radical in the denominator anymore. When you multiply something by 1, the value doesn't change. So we are going to take this answer, which is that, and we're going to multiply it by 1. But it's not going to look like 1. It's going to look like radical x over radical x. Anything over itself is 1. And the reason is, when you multiply by radical x on the bottom, you get x to the 3rd. Radical x times radical x is radical x squared. If you can do this, we know we can break it up. If there are two things that are multiplied together under a radical, we know we can give them each their own. It works the other way also. If you have 2 underneath their own radical, then you can put them together underneath 1. So this would become, on the denominator, would become x to the 3rd square root of x squared. The top would be y to the 4th square root of x. They didn't really explain that very well right there. But hopefully you can see that square root of x times square root of x is square root of x squared. That's under the radical. Which is x. And so if this right here becomes x, and you already have an x to the 3rd, then x to the 3rd times that x would be x to the 4th. And then you have a radical on top. Let's do another one. I know that was a little messy. This one will be to the cube root. So if it's cube root, we do a cube root of 2 over cube root of 9x, give them their own cube root. Nothing's a perfect cube. Nine is almost a perfect cube. It's 3 squared, right? If I multiply it by another 3, now the reason I'm doing this is because I can't have a radical in the denominator. Okay, if I stop with this answer, I have a radical in the denominator, and I can't have that. So it would be nice if under that cube root I had a 3 to the third and an x to the third. If I had 3 to the third and x to the third under that denominator radical, then it would wipe itself out. But I don't. But I can make it that way as long as I multiply the top by the same thing, it'll work out. So I'm going to multiply the bottom by 3, the cube root of 3x squared. And so the result will be 27x to the third on the bottom. And then I just have to deal with whatever the top turns into. I'm not even worried about what the top turns into. My whole focus is trying to get all the radicals off the denominator. It may be messy on top. And that's fine as long as I don't have any radicals in the denominator. So this will become the 27x to the cube. And then the top became 6x squared. And then the 27x to the cube are 2 perfect cubes, so that breaks just into 3x. The top is going to stay like that because none of those are perfect cubes. Okay? Square root. Okay? So square root of x to the third, square root of x to the y to the seventh. So that would break up into square root of x to the third over, and I can break that up later. What do I do with that? What does that turn into? Y cubed squared y. So that turns into y cubed square root of y on the bottom. The top was what, x root x. So if I rationalize the denominator, well, I'm not done because I didn't rationalize the denominator. So I need to multiply by whatever will get rid of this radical, square root y, over itself. Because these two together, when you multiply them, turns into just plain old y. So you have y times y to the third. There we go. There's where the y to the fourth came from. On the top, we got x times x squared, square root x times square root of y. These two can kind of share at the same house. It's not real straightforward. You gotta, it's like a puzzle. Okay, some pieces look like they fit together, but then in the end they don't. And sometimes you have to back up and start over. cube root of 8, cube root of 3y squared. Is 8 a perfect cube? Okay, let's take care of that. 2 cubed, right? 2 times 2 is 4 times 2 is 8. So that I can write the top as just a plain old 2. That makes, at least visually, it makes it a lot more simple. And in the bottom, I have a 3y squared. That's the cube. So 3 is nothing even squared. 3 times 3 times 3 is what I need. Okay? So I need to multiply by a 3 squared. I need to multiply by a cube root of a 3 squared. That'll give me a 3 to the third and a y to the first. That'll give me a y to the third. So when I multiply these two together in the denominator, I get a cube root of 3 to the third, y to the third, which will become just 3y. But I have to do the same thing to the top. But that doesn't matter too much. That just becomes 2 cube root of 9y, which can't be broken down. And I don't want to mess with it because it's in the numerator. So then the only thing this leads to, the top doesn't change. At the bottom, this cancels those two. Just left with 3y. So it looks like a C is what we're thinking, unless we made an error. Whew. Got it. 2's and the 3's, the things that are outside together is 6, and then the cube root. These two things can be multiplied together under the same cube root. And that just becomes 16 times 4, which is 4 to the third. Sometimes you see it, sometimes you don't. A to the third. 16 was 4 squared. And then I had another 4. And then I saw, and sometimes you see it, sometimes you don't, that it's a cube root, and so I need cube stuff, and so I left it as 4 cubed. And then that kind of helps me go into the next step, which is just going to be 6 times, those cancel, those cancel. 24a. Adding and subtracting on radicals. So it's different when it's addition and subtraction. You just can't put them under, you can't group them under the same radical. It's kind of like having like terms. You want to break the stuff underneath the radical down, but in the end, when you've broken it down as far as you can break it down, only the ones that have the same radicals attached to it are going to be able to combine together. So square root of 45 is going to break down into 9 times 5, and 9 will be 3 squared. 80 breaks down into 16 times 5. 16 is 4 squared. 20 breaks down into 2 squared times 5, or 4 times 5. So each one you break down into their own factors of squares as much as possible. I think you can skip that step and go straight to taking this 3 squared out, multiplying it by that 3, taking this 4 squared out, multiplying it by that 5. Taking this 2 squared out and multiplying it by the 4. And leaving in this 5, this 5, and this 5. 2 squared came out. 4 squared came out. 3 squared came out. That's just a 3 and a 4 and a 2. So we end up getting 9 root 5, negative 20 root 5, and 8 root 5. All of them have the same root. All of them have the same root, so that they're basically like all like terms. It's kind of like having 9x minus 20x plus 8x. You can add just the coefficients up. 9 minus 20 plus 8 is a negative 3 root 5s. Tells me how many root 5s do I have. Starting with 9, took away 20, added 8, left with negative 3 root 5s. Practice this one. What's a perfect square that's a factor of 75? 25 times 3. The 25 comes out as its square root. I'm going to skip some steps. 25 comes out as the square root of 25. So it'll be 3 times 5. Square root of 3 stays inside. Follow that? Yeah? And then, nothing to do with that except to bring them down plus root 3. So we have 15 root 3s, and they all happen to be root 3s. If they weren't all root 3s, then you only put the ones together that have the same roots, and you leave the others separate. Well, 15 minus 8 plus 1. 8? I think. 15 minus 8 is 7. Plus 1 be 8. We're hoping for D. Good. This 3 is kind of like a regular old 3. And if root 3 was kind of like my x, then I have a minus x. Now, if you had to multiply those together, you would have to do some FOIL to get it done. Okay? But the only difference is, if I ever multiplied by x, it would just become x squared. But if I multiply root 3 by root 3, it just becomes 3. I probably lost you on that. Let's go through this and FOIL it. So FOIL would take 2 root 3 times 3. The first terms. That's what the F stands for. First. 2 root 3 times 3. 2 root 3 times 3. Then we have the outside terms, which is 2 root 3 Okay, this guy right here should be, it's kind of misleading. That negative sign should actually be on that. I would prefer it to be written as plus 2 root 3 times negative root 3, because that negative is on the root 3. Whatever, it's going to end up being the same. And then the inside is 3 root 5 times 3. That's these two that are on the inside closest together. And then you have your last terms. That one times that one. So when you multiply them together, after you figure out who's going to get multiplied together, then when you actually do the multiplication, you get 6 root 3 minus 2 root 3, then root 3 would be minus 2 root 3 squared. 3 times 3 is 9 root 5. And then 3 root 5 times root 3 would be times root 15. This one is going to change. Square root of root 3 squared, square root of 3 squared is just 3. So that'll become a negative 6. Nothing else is going to change. But then I need to combine. Well, I don't really have anything to combine. This is a root 3. This it doesn't have any roots. This is a root 5. This is a root 15. None of them can be broken down, and so they're going to all have to stay separate because none of them would be considered to be like terms. Start with that. What does that become? 10 root 5. What does that become? Negative 2, right, root 35. What does that become? Root 6. And then square root of 42. Now, the only thing we need to do now is there a perfect square that's a factor of 35? 35 is just 5 times 7. 7 can't be broken down. 5 can't be broken down. So no. 42. Does 42 have a perfect square that's a factor? 42 is the same as 2 times what? 21? Right? So 42 breaks down into 2 and 21, and 21 just breaks down into 2 or 3 times 7. So 42 is just 2 times 3 times 7. And when I do a prime factorization, if I don't have 2 of the same thing, at least 2 of the same thing, then it's it's not going to have any factors that are perfect squares. So that one has to stay the same. So then the whole thing just stays just like that. I don't even, all of them are different. I can't put any 2 of these together because all the radicals are different. I can't break any down because none of those numbers inside the radicals have perfect square factors. So I have to just go with, come on D, yes. You look at the bottom, starting with number 28, the denominator has a radical, but it's also a binomial. It's kind of considered to be a binomial. You got 2 terms in it, subtracted. And how do you get rid of the radical like that? If I just try to multiply by radical 2, then I get rid of that radical 2, but it ends up being on the A, on the right. So here's what we talk about using a conjugate to rationalize the denominator. So you need to, if you're sleeping right now, please wake up and write this down. A conjugate. When you have a denominator of A, square root of 2 minus A, your conjugate, the thing that will help you rationalize the denominator, is, it's a lot of words to write down. Basically, you just need You don't need to write all of that down. We just need to figure out to use the conjugate to simplify that. We'll run out of time. If your denominator is a squared root of 2 minus a, the conjugate of that will be a squared root of 2 plus a. That's all you do. You change the sign of the middle guy. You change the sign in the middle. And then when you multiply, the numerator may get messy, but the denominator, a squared root of 2 minus a times a squared root of 2 plus a, the square root will end up disappearing and going away. Okay? When you use FOIL, it'll disappear and go away. Similar to what happened when we had the factor difference of 2 squares. So a squared root of 2 plus a and a squared root of 2 minus a will be considered conjugates. When you FOIL it out, it looks messy at first. But then what happens with these two things? A positive and a negative of the same thing. Cancel. And what happens here? If you square a square root of 2, it just becomes 2. So that's how that radical goes away. Not much explanation in between this step and this step, but that's what happens. The radical goes away in the denominator. When you multiply by the conjugate, the radical goes away in the denominator. You have to do it on top and bottom, remember. Oh, they went a step further. Everything has a factor of a squared. So the a squareds can cancel off of each other. And you're just left with that, which reduces to just square root of 2 plus 1.